Standard 9 Science and Technology. Chapter number 3 Current Electricity. Introduction. All around us. Electricity is of utmost importance in the modern world. We depend on it for almost everything in our day-to-day life. In order to avoid the inconvenience faced due to failure of power supply, hospitals, banks, offices and private institutions make alternative arrangements with the help of generators. Electricity is used for running electric furnaces, electric motors and several other instruments used in industries. Domestic appliances like the fridge, electric oven, mixer, fans, washing machines, vacuum cleaner, roti maker, etc. have helped us by saving time and labor. All these devices cannot be run without electricity. Not only human beings, but some animals also use electricity. For example, fishes such as eels use electricity to catch their prey and also for self-defense. The lightning that strikes the earth is an excellent example of natural flow of electricity. What if we could collect and store this electricity? Can you recall? You must have seen a waterfall. Which way does the water flow? For the generation of electricity, water is released from a dam at a higher level and because of gravity, it falls to a lower level. Thus, as we know, the direction of flow of water between 2 points depends on the level of the 2 points. Potential and potential difference. Try this. Equipment, 2 plastic bottles, rubber tube, clamp, water. Procedure. Set up the experiment as shown in figure. Then remove the clamp from the rubber tube. Note your observations. Answer the following questions. 1. What happens when the clamp is removed? 2. Does the water stop flowing? Why? 3. What will you do to keep the water flowing for a longer duration? Just like water, the flow of
a conductor
electric
is
charge
connected to each
between
terminal
2
of a battery.
points depends
Electrons
on a
start
kind
to
of
move,
electric level
traveling from
at
the negative
those
terminal
points.
towards the positive
This
terminal.
level is called
This is
electric
electricity.
potential.
The electrons
A
actually
positive
move from
charge
atom to
flows
electrons.
from
They
a
travel
point
through the
of
conductor.
higher
Our light bulb does
potential
2 things.
to a
This
point
is it
of
introduces some
lower
resistance into the
potential.
circuit,
Never connect a
producing
short
We
short
have
metal
seen
wires between
earlier
the terminals
that
of a battery.
electricity
This is
flows
a short
due
circuit.
to the
Electrical energy
conduction
and wire
of
energy.
negatively charged electrons.
Our circuit also
Electrons flow from the point of lower potential to a point of higher potential. A lightning strike is the flow of electrons from point of lower, that is negative potential, on the clouds to the point of higher, that is zero potential, on the earth. We shall study the definition of electric potential in higher standards. The difference between the values of potentials at 2 points A and B is called the potential difference between them. In the figure, conductor A is at a higher potential than conductor B. When these two are connected by a conducting wire, a potential difference is created between its two ends, and electrons will flow from B to A through the wire. This flow will continue until the two conductors A and B have the same potential, that is, until their potential difference becomes zero. Only then will the flow of electrons stop. Work has to be done against the electric field to take a positive charge from a point of lower potential to a point of higher potential. Potential difference of a cell. The difference in potential between the positive and negative terminals of a cell is the potential difference of that cell. This potential difference is caused by chemical reactions occurring inside the cell. The potential difference sets the electrons in motion and results in the flow of electricity through a conducting wire connected to the two ends of the cell. The amount of work done to carry a unit positive charge from point A to point B is called the electric potential difference between the 2 points. Potential difference between 2 points is equal to work upon total charge transferred. V is equal to W upon Q. 1 V is equal to 1 joule upon 1 coulomb. The unit of potential difference in the SI system is volt. An introduction to scientists. The Italian scientist Alessandro Volta constructed the first electric cell. The unit of potential difference is named volt in his honor. Do you know? Very small values of potential difference are expressed in the following units. 1 MV millivolt is equal to 10 raised to minus 3 V. 2 1 mu V microvolt is equal to 10 raised to minus 6 V. Large values of potential difference are expressed in the following units. 1 kV kilovolt is equal to 10 raised to 3 V. 2 1 MV megavolt is equal to 10 raised to 6 V. Free electrons. Every atom of a metallic conductor has one or more outermost electrons which are very weakly bound to the nucleus. These are called free electrons. As shown in figure, these electrons can easily move from one part of a conductor to its other parts. The negative charge of the electrons also gets transferred as a result of this motion. The free electrons in a conductor are the carriers of negative charge. Current flowing through a wire. If a conducting wire is not connected to a cell, its free electrons move randomly in all directions in the space between the atoms. When we connect the ends of the wire to the two terminals of a cell, electric force acts on the electrons. Being negatively charged, they start moving from the negative, that is the lower potential, to the positive, that is the higher potential, terminal of the cell, as shown in figure. Due to the flow of these electrons, current starts to flow through the wire. This motion of electrons is irregular, but there is a definite non-zero value to their average velocity. Electric current. An electric current is the flow of electrons through a conductor. Quantitatively, current, that is I, is defined as the charge passing through a conductor in unit time. If charge Q is flowing through cross-section of a conductor in time t, then the current is equal to I, which is equal to Q upon T. The unit of charge in SI units is coulomb C. current is expressed in ampere A. The charge of one electron is 1.6 multiplied by 10 raised to minus 19 coulomb. Ampere. 1 ampere current is said to flow in a conductor if 1 coulomb charge flows through it every second. 1A is equal to 1C upon 1S. Even though the electrons move from the negative end to the positive end, conventionally the direction of current flow is taken to be opposite of the direction of flow of electrons, that is, from the positive end to the negative end of a cell. Do you know? Very small values of current are expressed in the following units. 1 MA milliampere is equal to 10 raised to minus 3 ampere. 2 1 mu A microampere is equal to 10 raised to minus 6 ampere. The French mathematician and scientist Ampere conducted a number of experiments on electricity. Today, we can measure the current flowing in a conductor only because of his extraordinary work. The unit of current is called ampere in recognition of his great work. Example: a current of 0.4 ampere flows through a conductor for 5 minutes. How much charge would have passed through the conductor? Given I is equal to 0.4 ampere, T is equal to 5 minutes, which is equal to 5 multiplied by 60 seconds, which is equal to 300 seconds. Formula: Q is equal to I multiplied by T. Q is equal to 0.4 ampere multiplied by 300 seconds. Q is equal to 120 coulomb. Therefore, charge passing through the conductor is equal to 120 coulomb. Using ICT. Study current electricity and other scientific concepts with the help of simulation technology. Website: www.fet.colorado.edu, www.edumedia-sciences.com. Find some more websites like the ones mentioned above and share them with others. Resistance and Ohm's Law. Ohm's Law. The relationship between the current flowing through a wire, that is I, and the potential difference across its ends, that is V, can be obtained from the law that was given by the German scientist George Simon Ohm. If the physical state of a conductor remains constant, the current I flowing through it is directly proportional to the potential difference V between its two ends. I is directly proportional to V. I is equal to kV, where K is equal to constant of proportionality. I multiplied by 1 upon K is equal to V. 1 upon K is equal to R, which is equal to resistance of the conductor. I multiplied by R is equal to V, hence V is equal to IR, or R is equal to V upon I. This is known as Ohm's Law. We can obtain the SI unit of resistance from the formula. Potential difference and current are measured in volts and amperes respectively. The unit of resistance is called ohm. It is indicated by the symbol. Therefore, 1 volt upon 1 ampere is equal to 1 ohm. Physical state of a conductor means its length, area of cross-section, temperature and the material it is made up of. Resistance of 1 ohm. If 1 ampere current flows through a conductor when 1 volt potential difference is applied between its ends, then the resistance of the conductor is 1 ohm. Resistance and resistivity of a conductor. As shown in figure, there are a large number of free electrons in a conductor. They are constantly in random motion. When a potential difference is applied between the two ends of the conductor, these electrons start moving from the end at the lower potential to the end at the higher potential. This directional motion of the electrons causes the flow of current. Moving electrons strike the atoms and ions which lie along their path. Such collisions cause hindrance to the flow of electrons and oppose the current. This hindrance is called the resistance of the conductor. An introduction to scientists. German physicist Georg Simon Ohm established a law for measuring the resistance of a conductor. In his honor, the unit of resistance is called the ohm. Resistivity. At a given temperature, the resistance, that is R, of a conductor depends on its length, that is L, area of cross-section, that is A, and the material it is made of. If the resistance of a conductor is R, then R is directly proportional to L. Also, R is inversely proportional to 1 upon A. Therefore, R is directly proportional to L upon A. R is equal to rho L upon A. Rho is the constant of proportionality and is called the resistivity of the material. The unit of resistivity in SI units is ohm meter. Resistivity is a specific property of a material and different materials have different resistivity. Resistivity of some materials. Copper 1.7 multiplied by 10 raised to minus 8 ohm meter. Nichrome 1.1 multiplied by 10 raised to minus 6 ohm meter. Diamond 1.62 multiplied by 10 raised to 13 to 1.62 multiplied by 10 raised to 18 ohm meter. Think about it. How will you prove that the unit of resistivity is ohm m? Electric circuit. A continuous path of an electric current through conducting wires connected to the two ends of a cell and other resistances is called an electric circuit. A circuit is depicted by a figure. This figure shows how different components are to be connected in the circuit by using special symbols for each of the components. Such a figure is called an electric circuit diagram. In the circuit in figure, an ammeter is used to measure current and a voltmeter to measure the potential difference between the two ends of a resistor. As the voltmeter has a very high resistance, only very small current flows through it. Observe. 1. Point out the mistakes in figures. 2. Why are the bulbs in figures B, C and D not lighting up. Symbols for components of an electric circuit and their uses. Component, electric cell. Picture. Symbol. Use. To apply a potential difference between two ends of a conductor. Component, battery, collection of a number of cells. Picture. Symbol. Use. To apply a larger potential difference between two ends of a conductor. Component, open tap key or plug key. Picture. Symbol. Use. To stop the flow of current flowing in a circuit by disconnecting two ends of a wire. Component, closed tap key or plug key. Picture. Symbol. Use. To start the flow of current in a circuit by connecting two ends of a wire. Component, connecting or conducting wires. Picture. Symbol. Use. To connect various components in the circuit. Component, crossing wires. Picture. Symbol. Use. To show wires which cross but are not connected. Component, light bulb. Picture. Symbol. Use. To test the flow of electricity, lighted, current is flowing, unlighted, current is not flowing. Component, resistance. Picture. Symbol. Use. To control the flow of current in the circuit. Component, variable resistance. Picture. Symbol. Use. To change the resistance as required and thereby control the current. Component, ammeter. Picture. Symbol. Use. To measure the current flowing in the circuit. Component, voltmeter. Picture. Symbol. Use. To measure the potential difference between 2 points in the circuit. Try this. Material, copper and aluminium wires, glass rod, rubber. Method, make connections as shown in figure. First, connect a copper wire between points A and B and measure the current in the circuit. Then, in place of the copper wire, connect an aluminium wire, glass rod, rubber, etc. one at a time and measure the current each time. Compare the values of the current in different cases. Conductors and insulators. We have learnt about the resistance to an electric current. We can divide substances into conductors and insulators or bad conductors. Conductors. Those substances which have very low resistance are called conductors. Current can flow easily through such materials. Insulators. Those substances which have extremely high resistance and through which current cannot flow are called insulators. 1. Why are some substances conductors while others are insulators? 2. Why can our body conduct electricity? Make a list of conductors and insulators you see around you. Experimental proof of Ohm's Law. Try this. Material: 4 cells of 1 V each, ammeter, voltmeter, conducting wires, nichrome wire, plug key. Procedure: 1. Set up the circuit as shown in figure. 2. Use the nichrome wire XY as the resistance. 3. Connect one of the 4 cells as shown in figure A. Take readings of ammeter and voltmeter and enter them in the table. 4. Now add the rest of the cells one by one as shown in figures B, C and D. Enter the readings in the table for each case. 5. Determine the values of V upon I for each case. 6. Draw a graph between current and potential difference and study it. Using ICT. Using the internet, find out about the different softwares used to solve mathematical problems and use them to solve problems given in this and other chapters. Solved examples: Ohm's Law and resistivity. Example 1. The resistance of the filament in a light bulb is 1000 ohm. If the bulb is fed by a current from a source of potential difference 230 volt, how much current will flow through it? Given R is equal to 1000 ohm, V is equal to 230 volt. Formula: I is equal to V upon R. Therefore, I is equal to 230 volt upon 1000 ohm, which is equal to 0.23 ampere. Therefore, the current flowing through the filament of the bulb is equal to 0.23 ampere. Example 2. The length of a conducting wire is 50 centimeters and its radius is 0.5 millimeters. If its resistance is 30 ohm, what is the resistivity of its material? Given L is equal to 50 centimeters, which is equal to 50 multiplied by 10 raised to minus 2 meters. R is equal to 0.5 millimeters, which is equal to 0.5 multiplied by 10 raised to minus 3 meters, which is equal to 5 multiplied by 10 raised to minus 4 meters, and R is equal to 30 ohm. Resistivity is equal to RA upon L, and A is equal to pi R square. Therefore, rho is equal to R pi R square upon L, which is equal to 30 multiplied by 3.14 multiplied by 5 multiplied by 10 raised to minus 4 square upon 50 multiplied by 10 raised to minus 2, which is equal to 30 multiplied by 3.14 multiplied by 25 multiplied by 10 raised to minus 8 upon 50 multiplied by 10 raised to minus 2, which is equal to 47.1 multiplied by 10 raised to minus 6 ohm meter, which is equal to 4.71 multiplied by 10 raised to minus 5 ohm meter. Therefore, resistivity of the wire is 4.71 multiplied by 10 raised to minus 5 ohm meter. Example 3. A current of 0.24 ampere flows through a conductor when a potential difference of 24 volt is applied between its two ends. What is its resistance? Given V is equal to 24 volt, I is equal to 0.24 ampere. Formula: R is equal to V upon I. Therefore, I is equal to 24 volt upon 0.24 ampere. R is equal to 100 ohm. The resistance of the conductor is 100 ohm. Example 4. Determine the current that will flow when a potential difference of 33 volt is applied between two ends of an appliance having a resistance of 110 ohm. If the same current is to flow through an appliance having a resistance of 500 ohm, how much potential difference should be applied across its two ends? Given V is equal to 33 volt and R is equal to 110 ohm. In the first case, I is equal to V upon R, which is equal to 33 upon 110. Therefore, I is equal to 0.3 ampere. The current flowing through the appliance is equal to 0.3 ampere. In the second case, I is equal to 0.3 ampere, R is equal to 500 ohm, V is equal to IR, which is equal to 0.3 multiplied by 500 volt, which is equal to 150 volt. The required potential difference between its two ends is equal to 150 volt. Example 5. Determine the resistance of a copper wire having a length of 1 kilometer and diameter of 0.5 millimeter. Given ρ is equal to resistivity of copper, which is equal to 1.7 multiplied by 10 raised to minus 8 ohm meter. Converting all measures into meters, L is equal to 1 kilometer, which is equal to 1000 meters, which is equal to 10 raised to 3 meters. D is equal to 0.5 millimeter, which is equal to 0.5 multiplied by 10 raised to minus 3 meters. If R is the radius of the wire, then its area of cross section A is equal to pi r square. Therefore, A is equal to pi multiplied by D upon 2 square, which is equal to pi upon 4, 0.5 multiplied by 10 minus 3 square meter square, which is equal to 0.2 multiplied by 10 minus 6 meter square. R is equal to ρ L upon A, which is equal to 1.7 multiplied by 10 raised to minus 8 ohm meter multiplied by 10 raised to 3 meter upon 0.2 multiplied by 10 raised to minus 6 meter square is equal to 85 ohm. System of resistors and effective resistance. A resistor is a two-ended component having a given amount of resistance between its two ends. In several electrical devices, a number of resistors are connected together in different ways. Ohm's law is applicable to all such conducted resistors. Resistors in series. Study figure. You can see that the ends of the three resistors are connected so that they follow one after the other in a single line. These resistors are said to be connected in series. In such an arrangement, the same current flows through each resistor. The value of current is I, and the potential difference between C and D is V. The three resistors R1, R2 and R3 are connected in series in the circuit. Let the voltages across them be V1, V2 and V3 respectively. Then V is equal to V1 plus V2 plus V3, 1. If Rs, S for series, is the effective resistance between C and D, then according to Ohm's law, V is equal to IRS, V1 is equal to IR1, V2 is equal to IR2 and V3 is equal to IR3. Substituting all these in equation 1, we get IRS is equal to IR1 plus IR2 plus IR3. RS is equal to R1 plus R2 plus R3. If n resistors are connected in series, then Rs is equal to R1 plus R2 plus R3 plus up to Rn. If resistors are connected in series, 1. The same current flows through each resistor. 2. The effective resistance of the resistors is equal to the sum of their individual resistances. 3. The potential difference between the two extremes of the arrangement is equal to the sum of the potential differences across individual resistors. 4. The effective resistance is larger than each of the individual resistances. 5. This arrangement is used to increase the resistance in a circuit. Do you know? When resistors are connected in series, they are connected one after another. If any one of them does not function, the circuit breaks and there is no flow of electricity. If two bulbs are connected in series, they will both give less light than if they had been connected individually. If three bulbs are connected in series, their light output will decrease further. Think about it. What is the reason behind this? Solved examples for resistors in series. Example 1. 3 resistors having resistances of 15 ohm, 3 ohm and 4 ohm are connected in series. What is the effective resistance in the circuit? Given R1 is equal to 15 ohm, R2 is equal to 3 ohm, R3 is equal to 4 ohm. Effective resistance Rs is equal to R1 plus R2 plus R3, which is equal to 15 plus 3 plus 4, which is equal to 22 ohm. Therefore, the effective resistance in the circuit is equal to 22 ohm. Example 2. 2 resistors having resistances of 16 ohm and 14 ohm are connected in series. If a potential difference of 18 volt is applied across them, calculate the current flowing through the circuit and the potential difference across each individual resistor. Given R1 is equal to 16 ohm and R2 is equal to 14 ohm, Rs is equal to 14 ohm plus 16 ohm, which is equal to 30 ohm. Let the current flowing through the circuit be I and the potential differences across 16 ohm and 14 ohm be V1 and V2 respectively. V is equal to IR. V is equal to V1 plus V2, which is equal to 18 volt. I is equal to V upon R, which is equal to 18 volt upon 30 ohm. Therefore, I is equal to 0.6 ampere. V1 is equal to IR1. V1 is equal to 0.6 multiplied by 16, which is equal to 9.6 volt. V2 is equal to IR2, which is equal to 0.6 multiplied by 14, which is equal to 8.4 volt. Therefore, the current flowing in the circuit is 0.6 ampere and the potential differences across the resistances 16 ohm and 14 ohm are 9.6 volt and 8.4 volt respectively. Do you know? The resistance of some conductors becomes nearly zero if their temperature is decreased up to a certain value close to 0 K. Such conductors are called superconductors. Some conductors do not obey Ohm's law. Such conductors are called non-ohmic conductors. Resistors in parallel. Resistors are said to be connected in parallel when their ends are connected at both sides as shown in figure. The figure shows three resistors R1, R2 and R3 connected in parallel between points C and D. V is the potential difference between C and D. Let I1, I2 and I3 be the currents flowing through R1, R2 and R3 respectively. Then the total current flowing through the circuit is I is equal to I1 plus I2 plus I3 1. Let Rp, P for parallel, be the effective resistance between C and D. According to Ohm's law, I is equal to V upon Rp. Similarly, I1 is equal to V upon R1. I2 is equal to V upon R2. I3 is equal to V upon R3. Substituting these in equation 1, V upon Rp is equal to V upon R1 plus V upon R2 plus V upon R3. Therefore, 1 upon Rp is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. If n resistors are connected in parallel, 1 upon Rp is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3 up to 1 upon Rn. Even if any one of the several bulbs connected in parallel becomes non-functional because of some damage to its filament, the circuit does not break as the current flows through the other paths and the rest of the bulbs light up. When several bulbs are connected in parallel, they emit the same amount of light as when they are connected individually in the circuit, while bulbs connected in series emit less light than when connected individually. If a number of resistors are connected in parallel, 1. The inverse of the effective resistance is equal to the sum of the inverses of individual resistances. 2. The current flowing through an individual resistor is proportional to the inverse of its resistance, and the total current flowing through the circuit is the sum of the currents flowing through individual resistors. 3. The potential difference across all resistors is the same. 4. The effective resistance of resistors connected in parallel is less than the least resistance of individual resistors. 5. This arrangement is used to reduce the resistance in a circuit. Solved examples of resistors in parallel. Example 1. Resistors having resistances of 15 ohm, 20 ohm and 10 ohm are connected in parallel. What is the effective resistance in the circuit? Given R1 is equal to 15 ohm, R2 is equal to 20 ohm and R3 is equal to 10 ohm, 1 upon Rp is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. 1 upon Rp is equal to 1 upon 15 plus 1 upon 20 plus 1 upon 10, which is equal to 4 plus 3 plus 6 upon 60, which is equal to 13 upon 60. Rp is equal to 60 upon 13, which is equal to 4.615 ohm. Therefore, effective resistance in the circuit is equal to 4.615 ohm, less than the least of the three, 10 ohm. Example 2. 3 resistors having resistances of 5 ohm, 10 ohm and 30 ohm are connected in parallel and a potential difference of 12 volt is applied across them. Obtain the current flowing through the circuit and through individual resistors. What is the effective resistance in the circuit? Given R1 is equal to 5 ohm, R2 is equal to 10 ohm and R3 is equal to 30 ohm, V is equal to 12 volt. I1 is equal to V upon R1, which is equal to 12 upon 5, which is equal to 2.4 ampere. I2 is equal to V upon R2, which is equal to 12 upon 10, which is equal to 1.2 ampere. I3 is equal to V upon R3, which is equal to 12 upon 30, which is equal to 0.4 ampere. I is equal to I1 plus I2 plus I3, which is equal to 2.4 plus 1.2 plus 0.4, which is equal to 4.0 ampere. 1 upon Rp is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3, which is equal to 1 upon 5 plus 1 upon 10 plus 1 upon 30, which is equal to 6 plus 3 plus 1 upon 30, which is equal to 10 upon 30, which is equal to 1 upon 3. Effective resistance in the circuit is equal to 3 ohm and the current flowing through the resistances 5 ohm, 10 ohm and 30 ohm is 2.4 ampere, 1.2 ampere and 0.4 ampere respectively. The total current flowing through the circuit is 4 ampere. Domestic electrical connections. The electricity in our homes is brought through the main conducting cable either from the electric pole or from underground cables. Usually, there are 3 wires in the cable. One is called the live wire, which brings in the current. It has a red or brown insulation. The other wire is called neutral wire, through which the current returns. It is blue or black. In India, the voltage difference between the live and neutral wires is about 220 volts. Both these wires are connected to the electric meter through a fuse. Through a main switch, they are connected to all the conducting wires inside the home so as to provide electricity to every room. In each separate circuit, various electrical appliances are connected between the live and neutral wires. The different appliances are connected in parallel and the potential difference across every appliance is the same. The third wire is called the earth wire and is of yellow or green color. This is connected to a metal plate buried deep underground near the house and is for safety purposes. Fuse wire. Fuse wire is used to protect domestic appliances. It is made of a mixture of substances and has a specific melting point. It is connected in series to the electric appliances. If for some reason the current in the circuit increases excessively, the fuse wire gets heated up and melts. The circuit gets broken and the flow of current stops, thus protecting the appliance. This wire is fitted in a groove in a body of porcelain like non-conducting material. For domestic use, fuse wires with upper limits of 1 ampere, 2 ampere, 3 ampere, 4 ampere, 5 ampere and 10 ampere are used. Precautions to be taken while using electricity. 1. Electric switches and sockets should be fitted at a height at which small children cannot reach and put pins or nails inside. Plug wires should not be pulled while removing a plug from its socket. 2. Before cleaning an electrical appliance, it should be switched off and its plug removed from the socket. 3. One's hands should be dry while handling an electrical appliance and, as far as possible, one should use footwear with rubber soles. As rubber is an insulator, it prevents the current from flowing through our body, thereby protecting it. 4. If a person gets an electric shock, you should not touch that person. You should switch off the main switch, and if the switch is too far or you do not know where it is located, then you should remove the plug from the socket if possible. If not, then you should use a wooden pole to push the person away from the electric wire.